Hey guys, it's Mr. Lowry. This is your function notation guided notes. This is for 11-4, November 4th. If you're in A cohort, if you're in B cohort, this will be for 11-5. These notes correspond with section 3.3 in your textbook. So if you want some additional examples or some more materials for reference, you can open up to that section 3.3 in your textbook, and that starts on page 122. Your homework for this section will also be out of the textbook, and that starts on page 125. And I'll go through a few of those problems with you as well. So for right now, we're going to look at these notes. If you were absent on one of those 2 days that I mentioned, then you're going to want to print this note sheet out and fill in the blanks, or you can make copies in your notebook just so that you have this for tests and quizzes. Okay. We talked last time about relations and functions and the different ways to relate them, or the different ways to express them. One of the ways that we can represent a function is a literal equation, or an equation with two variables. Okay, there's other ways to represent functions like tables and graphs and lists of coordinates and things like that, mapping diagrams, but this is one way we can do it. Okay. If we have an input value, we can use the equation to find a matching output value, so that blank is output, and a literal equation pairs inputs and outputs because it's a relation, and that's what relations do. All right, so find the value of y if x equals 4. In this case, 4 is the input value. Right? So what we would do is we would literally input 4. We put 4 in. So input means put it in. So in this case, we got y equals 3 times 4 minus 5. Oops, don't need that guy. Okay, so this is going to be 12 minus 5, which is going to be 7. So y equals 7 is the output value for this function when the input is 4. For this one, we'd do y equals 4 squared, and so we get y equals 16. And then for this one, we would have y equals 5 times 4 over 2, which will be 20 over 2, or 10, when we simplify. Okay, so notice that these literal equations, they all have two variables. If we have an input value, an x value, it will match us with a y value. It will give a matching output. Okay. One of the things that I wanted to get you guys to notice is that each of these functions uses y, and sometimes that can be a problem, right? So the next bullet point says, what are some of the limitations of using the y variable in all three times? Well, consider an answer. Like if we were looking at an answer, let's take the answer like y equals 7, for example. Okay, this answer is kind of meaningless unless we know where it came from. Okay, so y equals 7, did that come from this guy? Did that come from this guy? Did that come from this guy? It's hard to tell just by looking at an answer. Okay, so a statement like y equals 7 is meaningless unless we know two things. Okay, one, we want to know which function it came from. So what function did we use? Two, what was the input value? Okay, so the whole point of today, what we're going to talk about, is a new notation. It's called function notation. And the idea is to be a little bit more specific when we're talking about the answers that we have, or the outputs. So y equals 7 doesn't mean anything until I know what function I used and what the input was, because y is not always 7. Right? Here y is 7, here's y is 16, and here's y is 10. Depends on the function. Also, if I plugged in something besides 4 here, I wouldn't get 7. I'd get something different. So y equals 7 is dependent on which function and which input. Okay, so now we're going to talk about this notation. Now this right here, the way you say this is f of x. It looks kind of like f times x, but it's f of x, okay? So the notation f of x here is an alternative to using y. Now, we're used to y's, we like y's, but again, if we have a bunch of things and we label them all y, it's kind of hard to tell between the two. So we use a different notation, and f of x notation is what we're going to use. So it's an alternative to using y for outputs. Okay, it's pronounced f of x, and it doesn't mean f times x. It looks kind of like it, because if we had like 4 times 2, we know that's, if we wrote 4 and 2 like this, we'd know that's multiplying, that gives us 8. But in this context, this is not f times x. Okay, so if we have a function like this guy, y equals 3x minus 5, we can rewrite that with function notation. F of x equals 3x minus 5. Okay? So this just replaces the y, right? We just replace the y with an f of x, and it's the same function. Okay, let me kind of describe the different parts of this function. Okay, this right here represents the input value, and so does this. So x is the input. Okay, the letter f is what we name the function. Okay, we give it a letter name. This right here represents the output. It's kind of like a y value. Right, the whole thing, f of x together, represents the output. So what we can do with that is we can evaluate a function. We can use that notation, and I'll show you why it's kind of nice to have the function notation. Okay, so evaluate the function f of x equals 3x minus 5 for x equals 10. So what evaluate means, if you recall, is plug in the number and then do the operations. So what we do is we take the 10 for x and we put it here and we put it here. We replace both x's. Okay, so we got a 10 and we got a 10. Now on the right hand side, you'll notice that at every step, nothing changes. We don't do anything with this f of 10. It just stays the same. All this is a label. F of 10 is a label, but on the right hand side, we're actually evaluating. So 3 times 10 minus 5 would be 30 minus 5, which would be 25. So this right here, f of 10 equals 25, is actually a lot more information than just y equals 25. Okay, if you compare these two, y equals 25 doesn't tell me, what equation I plugged it into. It doesn't tell me what the input is. It just tells me an output value for some function. So if we give our function a different letter besides y, we name it something different, then we know which function we're referring to. We also know that there's the input and there's the output. When we evaluate this function, you see the 10 there at the beginning? Well, we lose it as we go. We lose track of what it was. That's what the left-hand side's for. We keep track of what the input was the whole entire time. So at the end of the problem, we know this is our answer, this is our output, but the function name is f, and this is what we put in. Okay? So the last statement means, like if we wanted to interpret this, when the input is 10, the output of the f function is 25. We can kind of use words to describe that. So function notation keeps track of the input, the function name, and the output all at the same time. That's what's nice about it. All right, now, if we have more than one function, we don't want to call them all f. That would give us the same problem that we had before where everything was called y. So we can use other letters like g or h to name a function if f is already taken. So f stands for function. That's kind of obvious. G and H are the letters that come after F in the alphabet. So you start with F, and then you're like, okay, next function we'll call G, and the next function after that we'll call H. So in this scenario here, we have the same 3 functions that we had at the very beginning of the notes here, right? It's these same guys, 3x minus 5, x squared, 5x over 2. We have all those same guys, but now we have different names for them. Instead of y, we have f of x, g of x, and h of x. So they all have different names. When we see something like this, find f of 4, this is actually just a really compact way of expressing information. What this means is evaluate the function f for an input of 4, or find the output of the function name f when the input is 4. So this is basically telling us to evaluate the function. Now we know specifically which one. We're going to use this one, not this one or this one, because it tells us f of 4, right? If they wanted us to use this function, it would say g of 4. If they wanted us to use this function, it would say h of 4. But since it says f of 4, we know we're using this guy. So what we would do here is we would take 4, that's our input, and we would put it in the function, right? We take this function, we put a 4 here and a 4 here, and that's what we got right here. All right, now notice again, the left-hand side doesn't change. This is just a label. It's a label that represents the function we're using and the input that we're using. We just leave it there to keep track of it. We have a 4 here, we can see our input, but as we go, we're going to lose track of that. So 3 times 4 minus 5 will be 12 minus 5, or 7. Okay, so let's compare f of 4 equals 7 with this statement that we had earlier. Right? Earlier we had y equals 7, but again doesn't really mean a whole lot because it's not clear which function I used and it's not clear which input I used. So you could say, okay, well, when is y 7? Under what conditions is y equal to 7? Okay, down here we solved that problem with function notation. Right? The f function is what we used, 4 is what we put in, and 7 is what we got out. So this is a lot more information. You can also kind of see that this represents a coordinate pair. Remember, functions pairs inputs and outputs, they make a pair. So the input 4 matches with the output of 7. This is another way of representing the coordinate 4, 7. Input, output. But we also know that it refers specifically to the f function. So this is one of the solutions for our f function. All right, now what we kind of want to do in this next one is we want to write in words how we would interpret this. And there's 3 pieces of information we need to include: the name of the function, the input, and the output. So we could say something like this. The output of the f function is 7 when the input is 4. Okay, that has all 3 pieces of information. So this little tiny mathematical statement packs in a whole bunch of information. Again, the function notation keeps track of the function name, the input, and the output. That's what's so nice about it. Okay. All right. Now this next one is kind of tricky because of the way the notes broke up, the page break. So when we look at these questions, we're still referring to the same 3 functions. So I'm just going to write those down here. We had f of x equals 3x minus 5. We had g of x equals x squared. And we have h of x equals 5x over 2. So these are the same 3 functions we defined. It's just when you go to the next page, it's like you kind of lose track of them. Okay, so g of 3, what this means is g is the function, the function name, and -3 is the input. Okay, so this is saying use the g function and use an input of -3 and evaluate. So if the g function is x squared, g of -3 equals -3 squared. We just plug in -3 for both g's, or for both x's, excuse me, for both x's. Right? G of x equals x squared. Okay, so replace this x and this x with a -3 and a -3. The left side doesn't change. The left side is just a label, right? It tells you what function we're using and it tells you what input we're using, but we just simplify the right-hand side or evaluate the right-hand side. And since -3 times -3 is +9, there's our statement. Okay? G of -3 is equal to 9. If I put -3 in the g function, I get 9. Okay, h of 6, same idea. H is the function name, right? And then 6 is the input. So they're saying use the h function and use an input of 6. So if I take this function and I put a 6 here and a 6 here, I get h of 6 equals 5 times 6 over 2. And then the left-hand side says the same. We don't do anything with the left-hand side. Again, it's just a label. It reminds us that we're using the h function and that we're using an input of 6. So we keep that there. The right-hand side is what we evaluate. 5 times 6 is 30. 30 divided by 2 is 15. Okay, and then that is our statement. H of 6 is equal to 15. It's a complete statement with our input, our function name, and our output. Okay, now this next little bit is a little bit different. These next two problems are slightly different. Okay, so notice here I'm given input, and in here I'm not given the input. So it's an x. It's not a 6 or a 3. It's not a number, right? But what I am given is the output. So these two problems right here are evaluate problems. Okay, they give me the input, and I got to find the output. These two problems right here are going to be backwards. These are going to be solving problems. Okay, I'm going to be given the output, and I'm going to go back and find the input. Okay, so if we look at f of x, this is the f of x we're using, the same f of x. We can translate this back if we want to use y values. Okay, so let's take a look at this function here, f of x equals 3x minus 5. And just to kind of make it clear for us, we can move it back into y notation if that's what you're more comfortable with. Y equals 3x minus 5. And then it also says f of x equals 40. Or in other words, y is equal to 40. So they're saying if f of x equals 40, find x. Or if y is 40, or if the output is 40, find x. So here we have an output of 40. That means that 40 is equal to 3x minus 5. Right? So this y is 40. Or in other words, they're saying the output is 40. Find x. So we have ourselves an equation we need to solve. Since we're pretty good at solving two-step equations, this isn't too bad. We just have to understand function notation. Okay, so 45 equals 3x. I'm going to divide both sides by 3. And then we get 15 equals x, or x equals 15. Okay. You don't have to translate it to y's, but that's just, one way of doing it. So again, we're given output, we're supposed to find input. All right, in this one here, it's the same idea. The words are just different. Find the value of x. So again, find x when h of x equals 50. Find the value of x for which h of x equals 50. So again, we're given output. We got to find input. Okay, let's try to do it without translating to y's this time. Okay, here's h of x. H of x equals 5x over 2. And now they're telling us that h of x is 50. So what I can do is I can replace this h of x with this number. So I got 50 equals 5x over 2. Okay, so to solve this guy, multiply both sides by 2 to get rid of the 2 here. That would be 100 equals 5x. The 2 is going to cancel on the left, or on the right, excuse me. It's going to multiply the 50 on the left and get 100. Divide both sides by 5, and you're going to end up with 20 equals x, or x equals 20. Okay, so they're both solved problems. If they give you a number inside the parentheses, that's an input. If they give you a number outside and it's not inside there, it's going to be an output. Input goes inside the parentheses, output goes outside the parentheses. Okay. This next guy is just kind of interpreting functions. So in like a real world scenario, basically reading a statement, a mathematical statement, and translating it into real life. So in this case, f of t is a function, and it's the outside temperature in Fahrenheit t hours after 6 a.m. So some time goes by, the temperature changes. That's kind of what's going on here. There's two quantities. temperature and time. And we know that temperature is dependent on time, or temperature is a function of time, right? So temperature depends on how many hours have gone by. So what this is saying is the input is 0 hours, right? T is replaced with 0, and T stands for hours. This is 0 hours. 0 hours after 6 a.m. So 0 hours after 6 a.m., the temperature is 58 degrees. So 0 hours after 6 a.m., the temp is 58 degrees. All right, now, if you think about it, 0 hours after 6 a.m., that's still 6 a.m. So another way we would write this is the temperature at 6 a.m. is 58 degrees. That's probably the easiest way to express it. All right, so next thing, same idea. This 4 is just a time, right? F of t is a function in terms of time. The inside guy, the input, is time here. Right, so 4 hours after 6 a.m., the temp is 75 degrees. So 4 hours after 6 a.m. is 10 a.m. So we can kind of jump right to that one. The temperature at 10 a.m. is 75 degrees. All right, this one's kind of funky. 6 hours is the amount of time that has gone by, but we don't know the temperature, and that's okay. It's like n degrees, it's like a variable. Okay, so 6 hours after 6 a.m., the temperature is n degrees. Well, 6 hours after 6 a.m. would be 12 p.m. So it would be lunchtime. So the temperature 6 hours after 6 a.m., or in other words, 12 p.m., is n degrees. All right, now this one has an inequality symbol. This is a less than symbol. So what this is saying is the temperature after 3 hours is less than the temperature after 9 hours. But what is 3 hours after 6? That would be 6 plus 3, which would be 9. 9 a.m. Okay, 9 hours after 6 a.m. Well, you get 7. I'm going to count with my finger. 7, 8, 9, 10, 11, 12. 1, 2, 3. Okay, so 9 hours later, you're going to be at 3 p.m. So it's kind of weird in this case that the 3 kind of turns into 9 a.m. and the 9 kind of turns into a 3 a.m. That's kind of just a coincidence in this case. These don't normally switch. We're just talking about a time, an amount of hours after this time. So this would be the temp after 9 a.m. or sorry, the temp at 9 a.m. is less than the temp at 3 p.m. Okay, so we're just translating 3 hours later, 9 hours later to actual times. Okay, this last one we don't have a time given, so this would be the temperature m hours after 6 a.m. is 81 degrees, and I can't really add m to 6, so this would just be the temperature is 81 degrees m hours after 6 a.m. I don't know what that time is, so I'm just going to leave it. Okay, the next one is very, very similar, so I'm not going to run through that whole thing, but I just do want to point out this symbol right here. It's kind of a wavy equal sign. This means approximately. Okay, so it's like about. But this is kind of a very similar scenario to the last one. Okay, last thing we need to talk about here is graphing. Okay, so in this case here, this graph is the function f. So we just name it f. We don't have to name it f. We can name it g or h or something else. But since we're kind of starting over here, we'll just start with an f for function. All right. So f of x is the output value, or remember that's a y value, when the input is x. So we're still using the same function notation. We're just doing it with graphs, okay? So this is the x-axis, and this is the f of x axis. Now, we really usually call that the y-axis, but with function notation, we might want to consider f of x as like a different way of labeling. Okay, so when you see something like this, f of 4, that's kind of like what we saw before. What this is asking for is what is the output of the f function when the input is 4. So you want to find the output value, y value, for an x value of 4. Okay, so let's say I didn't have this. This is actually the answer here. But let's just say you had f of 4. Okay, well, this is the function name, and this is the input, right? The number in the parentheses is the input. So what we have here is we have 4 comma something, 4 comma question mark, right? We need to find that output value, that y value. So if you go over to 4 and you go up to the graph, you see, oh, an input of 4 gives me an output of 2, or an x of 4 gives me a y of 2. So this mystery number here, this output, is 2. So the full statement here would be f of 4 equals 2, but that's kind of like the point 4 comma 2. Okay, next one, f of negative 3. So again, negative 3 is your input. Okay, that's the x value. So this is saying we got a negative 3 comma something as a coordinate, right? We're looking for this coordinate somewhere. Negative 3 comma question mark. We're looking for the output value. Okay, so we look at the f function. We find negative 3 on the x-axis, and the output value, the y value, is 0. So f of negative 3 equals 0. That's the new notation. Now, if we wrote it as a point, we have this point, negative 3, 0, so we know negative 3 matches with 0. Sorry, that got cut off a little bit. Yeah, so input is negative 3. Output is what we don't know. We look at the graph. We find that point, negative 3, 0, and so that's our answer here. All right, so try these two on your own. Pause the video really quick. These next 3, I should say. And then we'll come back and check your answer. Okay, coming back from pausing, what you should see here is f of 3, input is 3. This is the input, which means we have a point that's 3 comma something, right? Input is the x value. So we go over here to the x, and we look for our function at x equals 3, and it's up at 1. So 3 comma 1. That means f of 3 equals 1. Okay, f of 4, or excuse me, f of negative 4 is negative 5. X is negative 4. Oh, sorry. Negative 2, excuse me. X is negative 4, y is negative 2. Okay, and then f of 1. This one's kind of weird, but if you go over to your graph and you go like halfway up, you're going to hit the graph there. So if your x is 1, your y is about 1/2. So f of 1 equals 1/2. Shoot, I cut it off again. Sorry. I keep looking back up at the graph. But yeah, f of 1 equals 1/2 your outputs there. So f of 1 equals 1/2. The next two are similar, but they're giving us different information. Okay, so you might see this wording sometimes. It's kind of weird. Find the value of x for which f of x equals 3. Okay, this means we have to find the input value that matches to an output value of 3. Okay, so what they just gave us, notice they didn't give us the number inside. They didn't give us input. They gave us output. Okay, this is the output now, or the y value, in other words. So we need to find the x value that goes with the y value of 3. So when we look back up at our graph, we got to look for a y value of 3. Okay, there's where y is 3. So what x value goes with that y value? 5. If x is 5, y is 3. Okay, so the missing input here, the x that we're trying to find, is 5. X equals 5. Okay, similar on the next two. We'll have to kind of jump back and forth here between the graph and the question. But the input is unknown, right? Find the value of x. We don't know the input. What we know is the output. So remember, if we're talking about the number and it's outside the parentheses, that's the output. Inside the parentheses is the input. Okay, so this is the output, or a y value of -4. So we need to go back to the graph, and we look at where y is -4. Okay, that's right here. So the input value, the x value that I need is -5. Right? To get down to -4, I need a value of -5. So back over here, we know that -5 goes with -4, and so x equals -5. That's the value of x we're looking for. Okay? Last one here. Again, they're giving us the output. The number's not in parentheses, it's not the input, it's the output. So that's giving us y. We want a value where we have blank comma 1. We want an x value for x equals, or for when y equals 1. So we go to our graph and we look at where y equals 1. But it looks like there's actually a few different numbers. If I were to draw a line at y equals 1, right, there's y equals 1, I got 3 different x values that make that happen. So 3 gives me an output of 1. I have this point 3, 1. Okay, 0 gives me an output of 1. I have this point 0, 1. And then this guy kind of in the middle, this is like -2.5, 1. So -2.5-ish also gives me an output of 1. So there's actually 3 possibilities here. All of these have a y value of 1 or an output of 1, and that's kind of what this question is asking you. When are you going to have an output of 1? Well, x can equal 3 or 0 or -2.5. Those are your options. Okay, so once again, just to kind of reiterate, the number inside the parentheses is the input. If they give you the input, that's the x value. Okay, if the number is not in the parentheses, like this, it's outside the parentheses, we don't know the input, we actually know the output, or the y value. All right, in the next video, this video kind of got a little bit long here, but I wanted to make sure that I hit all those notes for the guys that weren't in class today. Tune in for the next video. I'm going to go through your homework assignment and look at a couple problems from each one of those sections.